The true scale of J1407b's rings is not something your eyes were built to accept. Picture Saturn's rings gone, replaced by a structure so wide it would reach almost to the orbit of Venus, swallowing a third of the night sky whole. No telescope has ever photographed it directly. Every detail we know came from watching a single star flicker for 56 days in 2007. Tonight we follow that flicker back to the person who finally noticed it and toward a question about this planet that even its discoverers still cannot fully answer. In 2007, a wide-field camera scanning the southern sky recorded 56 days of dimming light from a star in the constellation Centaurus. Astronomers catalog it as 1 SWASP J140747, 93-394,542.6, but everyone just calls it J1407 now. A young, sun-like star roughly 434 light-years away. What that camera caught, without anyone realizing it yet, was the first confirmed evidence of rings around a world outside our solar system. A normal planetary transit looks almost nothing like this. When a planet the size of Jupiter crosses in front of its star, the star's light drops by a small, precise amount for a few hours, sometimes less than a day, then climbs back to where it started. The signal is short, and it is clean, because the planet is tiny compared to the star, and it moves quickly across our line of sight. The dimming at J1407 ran for 56 days. It didn't fall once and recover once. It dropped, partially climbed back, dropped again, over and over, in a jagged, uneven rhythm that stretched across nearly 2 months of nights. Layered on top of that slow overall fade were rapid flickers, brightness changing on time scales of tens of minutes, the way a signal carries static writing on top of its main pattern. Whatever passed in front of J1407 was not a single solid body. A solid planet, even a very large one, produces one smooth dip and one smooth recovery, because its edge is a simple curved line crossing the star's disk. This was different. The unevenness in the light curve meant the object blocking the star had internal structure, something with gaps in it, something made of many separate layers, each one letting through a slightly different amount of starlight as it passed. Picture holding a single sheet of cardboard in front of a lamp. The light drops once, evenly, and comes back once, evenly, when you pull the cardboard away. Now picture holding up a stack of window blinds instead, each slat set at a slightly different angle, with narrow gaps of open space between some of them. As you tilt that stack past the lamp, the light doesn't drop and recover cleanly. It flickers, brightens through the gaps, dims again where the slats overlap, in a pattern that changes depending on exactly which part of the stack is in front of the light at that instant. That's the mechanical signature astronomers were reading in J1407's light curve. Not a shadow with one edge, but a shadow built from dozens of overlapping bands, each contributing its own small variation to the total dimming. The star itself is worth understanding before we go further into what caused this, because its age turns out to be central to the whole story. J1407 is only a few million years old, which in stellar terms places it in early infancy. Our own sun formed about 4.5 billion years ago. If you compress the sun's entire life into a single 100-year human lifespan, J1407 would be measured in hours, not years. Stars this young are typically still surrounded by leftover material from their own formation, gas and dust and small solid bodies that haven't yet been swept up into finished planets. That raw, unsettled environment is exactly the kind of place where a structure with this much internal complexity could still exist because nothing around a star this young has had enough time to smooth itself out into something simple. The survey responsible for catching this signal, called Super WASP, wasn't designed to look for anything like it. Its purpose was to monitor huge numbers of stars for the short, repeating dips caused by ordinary gas giants passing in front of them, the kind of clean signal that computer algorithms can flag automatically without a human ever reading the raw chart. A 56-day anomaly with this much internal texture didn't match what the pipeline was built to recognize. It got recorded correctly and filed correctly, one unusual entry sitting among many thousands of ordinary stellar light curves, and then it waited for 3 years. Not because anyone had made an error, but because nothing about the automated system was built to flag data this strange as worth a second look. The chart existed, complete and accurate, describing a 56-day event that would eventually turn out to be one of the strangest structures ever confirmed outside our solar system, and for 3 years it sat exactly where it had been filed, unread by anyone who understood what they were looking at. That gap between when the data was recorded and when someone finally understood it says something specific about how large-scale astronomical surveys actually work. They aren't built to interpret. They're built to collect. The interpreting still has to happen inside a person's mind, and that only happens when someone chooses to go back through an archive with no promise that anything unusual is waiting there at all. By the close of 2007, this is what existed: a light curve with real, measurable internal structure recorded faithfully from a young star in Centaurus, with no explanation attached to it yet. Nobody had confirmed what caused the dimming. Nobody had connected it to rings, or to a planet, or to anything specific at all. There was only a shape in the data that didn't match the pattern astronomers expected, sitting quietly, waiting for someone with enough patience to look at it directly and ask what kind of object could possibly cast a shadow like that. What would it actually take to turn that shape into a real, physical structure? By 2010, that 56-day light curve had been sitting in the SuperWASP archive for 3 years, filed correctly, waiting for someone with a reason to open it again. That someone was Mark Pekot, a graduate student working with astronomer Eric Mamajek at the University of Rochester, and their project had nothing to do with rings or with strange, structured eclipses. They were building a catalog of young stars, tracking stellar ages across a region of sky, and J1407 was one entry among hundreds they needed to characterize. Cataloging a young star usually means checking a short list of properties: its brightness, its color, its rough position on a chart astronomers use to estimate stellar age. Most of that information comes from data that already exists in public archives, so the actual work is less about pointing a telescope and more about sitting with numbers other people collected years earlier, deciding what they mean. That's the part of astronomy that almost never gets talked about outside the field. A huge amount of discovery happens at a desk, hours spent scrolling through archived measurements from surveys built for entirely different purposes, looking for whatever pattern the original project wasn't designed to notice. When Pekot pulled up J1407's SuperWASP light curve as part of that routine check, the shape on the screen didn't match anything a young star's brightness should do. Young stars do vary. They flicker slightly as star spots rotate in and out of view, or dim briefly during small flaring events, small fluctuations that barely register against the baseline brightness. What Pekot was looking at instead was a 56-day collapse, deep and structured. Nothing like the gentle noise expected from a star of this type. This wasn't the data he'd opened the file to find. It was data that raised a completely different question than the one his project was supposed to answer. He brought it to Mamajek, and what followed wasn't a single dramatic realization. It was closer to an argument the two of them had with the evidence itself, testing explanation after explanation and watching each one fail against the details in the chart. A single large planet couldn't produce a signal this long or this jagged. Because a solid body of any reasonable size crosses a star's disk in hours, not weeks. An eclipsing binary star, two stars orbiting closely enough to periodically block each other, could, in theory, produce long eclipses, but the specific brightness pattern didn't match what two stellar disks passing in front of each other should look like. Each explanation they tried got measured directly against the shape of the dimming, and each one left some part of the curve unexplained. What eventually held up was stranger than either of those options. Something orbiting J1407 itself, not another star, was blocking the light, and that something had to be enormous, disc-shaped, and made of many separate rings rather than one solid surface. The rapid flickers riding on top of the slow 56-day fade were the signature of the object's edge structure, dozens of individual bands with slightly different densities, each one letting a different amount of starlight through as it crossed the star. A single opaque disk would produce one smooth shadow. This was a disk built from separated components, gaps and rings layered together, which meant whatever was orbiting J1407 had internal architecture, not a simple silhouette. Mamajek and Picard didn't publish a paper saying they had found rings around an exoplanet. Their 2012 paper described the object cautiously, proposing it might be a large circumplanetary disk, material that could eventually form moons around a young giant planet or possibly a brown dwarf, the category of object too massive to be called a planet, but too small to sustain the nuclear fusion that powers a true star. That caution matters because the data alone couldn't yet prove which of those categories the underlying object belonged to. A light curve tells you how much light was blocked and when. It doesn't hand you a label for what did the blocking. Assigning a firm identity before the evidence supported one would have been a guess dressed up as a conclusion, and neither of them was willing to make that trade. The distinction between a large planet and a brown dwarf isn't cosmetic. It comes down to mass, and to what mass allows an object to do inside itself. Jupiter, the largest planet in our solar system, holds roughly 1,000th the mass of our Sunday. A brown dwarf needs to reach somewhere around 13 times Jupiter's mass before its core gets hot and dense enough to briefly fuse deuterium, a heavier form of hydrogen, and even that fusion sputters out within a few million years rather than sustaining a star's steady burn for billions. Early mass estimates for the object around J1407 ranged from roughly 2 to as much as 40 times Jupiter's mass depending on the model used, a range wide enough to sit on either side of that dividing line. Getting the classification right required more than one estimate agreeing. It required years of follow-up work by multiple research groups, refining the mass, refining the models, before the picture came into sharper focus. There's something worth noticing in how differently this discovery unfolded compared to how discoveries get portrayed. No single instrument was built for this. No team set out looking for rings around anything. A graduate student doing routine cataloging work found a chart that didn't behave the way it was supposed to, and two researchers spent real time testing explanations against the evidence, rather than reaching for the most exciting one available. That patience, choosing an uncertain but defensible description over a confident but unsupported one, is the same discipline that let this discovery hold up under a decade of further scrutiny instead of collapsing the way overstated claims often do. By the time their 2012 paper was published, J1407 had a companion object with a name J1407b and a description cautious enough to survive contact with better data. What it didn't have yet was proof. The disk hypothesis explained the light curve reasonably well. But reasonably well isn't the same as confirmed, and confirming it meant someone had to take that shape in the data and turn it into an actual physical model, ring by ring. That work would fall to a different researcher, working with a different set of tools, and it would take the vague outline of a disk and turn it into something far more precise and far stranger than anyone in 2012 had yet described. What would it actually take to prove that shape was rings and not something else entirely? Proving a shape in starlight was actually a system of rings meant someone had to do something no telescope could do directly. Take a light curve and turn it into a physical model with real dimensions. That work fell largely to Matthew Kenworthy at Leiden Observatory in the Netherlands, working with Eric Mamajek's team years after the original 2012 paper had proposed only a cautious disk hypothesis. The problem Kenworthy faced sounds almost impossible stated plainly. No instrument on Earth or in orbit can resolve J1407b's surroundings as an actual image. The star and its companion sit so close together from our vantage point, and the whole system is so far away that even the most powerful telescopes see only a single point of light. Whatever is happening around J1407b has to be reconstructed entirely from how that one point of light changes brightness over time. Nothing to look at directly, only a sequence of numbers describing dimming and brightening, minute by minute, across 56 days. That constraint sounds limiting, but it's also exactly what makes the reconstruction possible. A ring system blocking a star doesn't just dim the light evenly. Each ring has its own width, its own density, its own distance from the central object, and each of those properties changes how much starlight passes through at any given moment as the system moves across our line of sight. If you model rings with different combinations of width and density and spacing, each combination produces a distinct, predictable pattern in the resulting light curve. The reverse is also true. Given a strange enough light curve, you can work backward, testing ring configurations against the real data until you find the one that reproduces it. Kenworthy described running this modeling process later, saying the details visible in the light curve were remarkable, an eclipse lasting weeks but showing rapid changes on timescales of minutes, changes caused by the fine internal structure of the rings themselves. That description points at something worth understanding clearly. The rapid flickering layered on top of the slow 56-day fade wasn't noise. It was information, encoding the exact width and spacing of individual rings, the same way a fingerprint encodes identity in its ridges and whorls. Reading that fingerprint required testing an enormous number of possible ring configurations against the observed dimming, adjusting radius, density, and gap placement until the model's predicted light curve matched what SuperWasp had actually recorded back in 2007. What came out of that modeling was a structure larger than almost anyone had expected going in. The rings extend out to roughly 0.6 astronomical units from J1407b, an astronomical unit being the average distance from Earth to our Sun, about 93 million miles. That puts the outer edge of J1407b's rings at a distance comparable to how far Venus orbits our own Sunday. If you could remove Saturn's rings and replace them with this system, keeping Saturn exactly where it sits in our solar system, the new rings would stretch out roughly to where Venus circles the Sun today. Saturn's actual rings, by comparison, extend only about 80,000 miles from the planet, a scale so much smaller that Kenworthy's team calculated the difference at somewhere around 200 times larger by radius. The model didn't stop at overall size. It resolved more than 30 individual rings within that structure, each one distinguishable by its own contribution to the light curve's fine flickering. Some rings were dense enough to block a substantial fraction of starlight passing through them. Others were thin, letting most of the light pass unobstructed. That variation in density across different rings is itself a clue, because uniform, evenly spaced material tends to settle into a smooth, undifferentiated disk over time. A system with this much internal variation, dense bands next to nearly empty gaps, suggests something is actively shaping it, carving out specific regions rather than leaving the material evenly distributed the way gravity alone would tend to arrange it. There's a particular kind of confidence this modeling approach earns, different from the confidence of a direct photograph, but not weaker for being different. A photograph shows you a result without necessarily explaining it. A model like Kenworthy's has to work the other direction, starting from raw physical assumptions about how light interacts with ring material, then testing whether those assumptions can reproduce every wrinkle in 56 days of real data. When a model built from first principles matches an observed pattern this intricate, in fine detail rather than just in broad strokes, that agreement carries real weight. It means the physical picture being proposed, dozens of rings extending out roughly to Venus's orbital distance, isn't just a story that fits the headline facts. It reproduces the actual texture of the evidence, minute by minute, across the entire 56-day event. None of this settled every question about the system. The total mass estimated within the rings came out to roughly 1 Earth mass, spread across a structure 200 times wider than Saturn's, meaning the material inside J1407b's rings is far more diffuse on average than Saturn's own, despite occupying vastly more space. The modeling also couldn't determine exactly what the ring particles are made of, whether ice, rock, dust, or some mixture, only that their combined effect on starlight matched a specific physical structure and scale. Kenworthy's own comment about what these rings would look like from Saturn's position captures the scale better than the raw numbers alone. Placed there, they would be visible at night with the naked eye, appearing many times larger across the sky than the full moon does from Earth. What the modeling did settle was the shape of the mystery going forward. This wasn't a single disk, a leftover cloud of material with no internal order. It was an organized system of more than 30 distinct rings, with real gaps carved between at least some of them, gaps that don't appear by accident in any ring system we've studied closely, including Saturn's own. Every gap in Saturn's rings that astronomers have successfully explained turned out to have the same underlying cause, something orbiting inside that gap, sweeping the space clear through its own gravity. If the same physics applies here, then somewhere inside J1407b's gaps, something large enough to clear a path through solid ring material is already moving. What would something have to weigh to carve a gap that wide, this far from any star? A gap in a ring system is never actually empty space by accident. Every clean, sharply bordered break astronomers have successfully explained inside Saturn's rings turns out to have the same underlying cause, something orbiting inside that gap, sweeping the space clear through its own gravity as it moves. The clearest example is the Cassini division, the wide dark band visible between Saturn's A and B rings, even through a small backyard telescope. That gap exists because the moon Mimas, orbiting just outside it, tugs on any ring particle that drifts into a matching resonant orbit and nudges it away, over and over, until the region empties out. When Kenworthy's ring model for J1407b resolved more than 30 distinct bands, at least one of them showed the same signature, a sharp interruption in the ring density rather than a gradual thinning. That kind of edge doesn't form on its own. Loose material drifting under gravity alone tends to spread and blur, not carve itself a clean boundary. A defined gap with sharp walls on both sides means something with real mass is actively holding that space open. The same mechanism at work in Saturn's rings, just scaled up to match a ring system 200 times larger. Estimating how much that something weighs comes from measuring the gap itself, its width, and how sharply its edges are defined. A small moon clears a narrow gap with soft, gradually fading edges, because its gravitational pull only reaches a short distance before it weakens too much to matter. A more massive body clears a wider gap with harder, more sharply defined boundaries, because its pull extends further and pushes material away more forcefully. Applying that relationship to the most prominent gap in J1407b's rings gives a mass estimate somewhere between that of Earth and Mars, and in some models, that single hidden body may account for as much as 80% of the total mass locked up in the entire ring system. If that estimate holds, it would make this the most massive moon ever inferred anywhere, larger than every moon orbiting every planet in our own solar system, including Ganymede, the largest moon around Jupiter. Nobody has ever seen this moon directly. Every conclusion about its existence comes from the shape of an absence, a gap in ring density inferred from a light curve recorded in 2007 and modeled years later. That's a different kind of evidence than a photograph, but it isn't weaker evidence just because it's indirect. The same reasoning correctly predicted moons inside Saturn's ring gaps decades before some of those moons were directly imaged by passing spacecraft. Gaps have been a reliable signature of hidden bodies for as long as astronomers have studied ring systems closely, which is part of why this particular gap, this far away and this poorly resolved, still counts as meaningful evidence rather than speculation dressed up as fact. If a body that massive really is orbiting inside J1407b's rings, its own motion would follow directly from where the gap sits. Applying basic orbital mechanics to the gap's distance from J1407b gives an estimated orbital period of roughly 2 years, meaning this hypothesized moon would complete one full circuit around its planet in about the time it takes Earth to circle the Sun twice. Compare that to our own moon, which orbits Earth in about 27 days, or to Ganymede, which takes about a week to circle Jupiter. A 2-year orbital period around a planet places this hypothesized moon much farther from J1407b than any comparable moon sits from its own planet in our solar system, consistent with a ring system whose total span already dwarfs anything nearby. The reason a ring system can hold enough raw material to build a moon like this comes down to how young the entire system still is. J1407 itself is only a few million years old, and planet-forming disks around stars this young typically still hold on to significant amounts of gas, dust, and small icy or rocky bodies that haven't yet finished accumulating into larger objects. Around older, more settled planets like Saturn, most of that raw material either got swept into moons long ago or dispersed entirely, leaving behind rings that are comparatively sparse and stable. J1407b's rings still carry roughly 1 Earth mass of material spread across a structure that size, which puts this system somewhere in an earlier, messier phase of the same process that shaped Saturn's moons billions of years ago. That framing changes what this ring system actually represents scientifically. For decades, planetary scientists theorized that giant planets like Jupiter and Saturn pass through an early phase where circumplanetary disks, material orbiting the planet rather than the star, gradually accreted into the moons we see today. That theory explained a lot about why gas giants tend to have multiple large moons instead of none, but it remained just that, a theoretical model with no confirmed example anywhere to test it against. J1407b changed that. If the gap in its rings really does mark an actively forming moon, this is the first system where astronomers can watch that predicted process happening directly, rather than only inferring it after the fact from moons that finished forming billions of years ago. There's a specific kind of scientific patience required to hold two things true at once here. The gap is real, measured directly from the light curve data, with enough confidence to trust its width and position. The moon inferred from that gap remains a model, consistent with the evidence, but not yet confirmed by any direct detection. Both of those facts sit comfortably next to each other in careful science. The evidence supports a specific, testable prediction. It doesn't yet supply a photograph, and pretending otherwise would trade real understanding for false certainty. Exactly the kind of overreach the astronomers who found this system have avoided at every step so far. If a moon that massive really is forming inside these rings, will it survive long enough to become a stable, permanent satellite? Or will something about this system, its youth, its enormous scale, the gravitational pull of the distant star, prevent that formation from ever finishing? The question hanging over that hidden moon, whether it will survive long enough to finish forming, turns out to depend on something researchers didn't expect to have to ask. Not whether there's enough raw material in the rings, there clearly is, but whether the rings themselves are stable enough to last that long in the first place. Stability for a ring system comes down to a tug-of-war between two forces. The planet's own gravity holds the rings in place, keeping ring particles in orbit rather than letting them drift away. But J1407b doesn't exist in isolation. It orbits close enough to its parent star that the star's gravity reaches out and pulls on those same ring particles too, competing with the planet for control over how they move. When researchers ran computer simulations testing how a ring system this size would behave under that competing pull, the results depended entirely on one detail nobody had settled yet: which direction the rings actually orbit relative to the planet's own motion around the star. If the rings orbit in the same direction as J1407b moves around its star, called a prograde orbit, the simulation showed something the researchers didn't expect going in. That configuration is unstable. The star's gravitational pull, working in the same rotational direction as the rings themselves, gradually strips material away, particle by particle, until the ring system disperses entirely. Not over millions of years either. The simulation suggested a prograde ring system this size, orbiting this close to a star, would come apart on a timescale far shorter than the age of the star system itself, shorter than the few million years J1407 has already existed. That result created a real problem, because the rings clearly still exist. Whatever configuration they're actually in, it has to be one that survives, and prograde orbital stability doesn't survive the math. The only alternative that holds up under simulation is retrograde motion, the rings orbiting in the opposite direction from the planet's own path around the star. In that configuration, the competing gravitational pulls partially cancel out rather than compound, and the rings can remain stable for a far longer stretch of time, long enough to plausibly still exist billions of years into the system's life, or at minimum, long enough to still be here after only a few million years of youth. Picture two people spinning a jump rope between them. If both people turn their wrists in the same direction, the rope whips around cleanly, building momentum with each pass, and anything caught in that motion gets flung outward with real force. Now picture one person turning their wrist one way while the other turns the opposite way. The rope doesn't build the same clean reinforcing momentum. The two motions partially fight each other, and the whole system settles into something calmer, less prone to flinging its contents outward. That's roughly the difference between a prograde and a retrograde ring system here. Prograde motion lets the star's pull reinforce the ring particles' existing momentum until they're thrown clear. Retrograde motion works against that momentum instead, damping it down rather than amplifying it, which is what lets the rings hold together over meaningful stretches of time. A retrograde ring orbit is possible, but it isn't the expected outcome of ordinary planet formation. Planets and their surrounding disks typically form together, spinning in the same direction as the material they condensed from, the same reason nearly every planet in our own solar system orbits the Sun in the same direction, and most of their moons orbit in the same direction as well. A ring system moving retrograde relative to its planet's orbit around the star suggests something unusual happened, either during formation or sometime afterward, that put the rings on a different rotational path than the planet took around its star. If a system this size, this close to a star, genuinely can't remain stable in a bound, prograde configuration, some researchers have suggested J1407b might not be gravitationally bound to its star's orbit in the traditional sense at all, that it could be a free-floating object, drifting rather than settled into a stable long-term orbit the way most confirmed exoplanets are. That possibility remains genuinely unresolved. It isn't the consensus explanation, and other researchers have pointed out that a stable retrograde configuration, however unusual, is enough on its own to explain why these rings still exist without requiring the more dramatic reclassification of the entire planet's relationship to its star. What both explanations share is an honest acknowledgement that something about this system doesn't fit the pattern astronomers expected before they modeled it closely. Either the rings occupy an unusual retrograde orbit that formed through some process not yet fully understood, or the whole system's relationship to its parent star needs reconsidering in ways that go beyond how the rings themselves are oriented. Neither option was on the table back in 2012, when the discovery paper described only a cautious disk hypothesis. The deeper researchers modeled this system, the more its stability turned out to depend on answering a question about the planet's fundamental nature, not just the rings sitting around it. A structure 200 times larger than Saturn's rings, carrying enough material to build one of the largest moons ever inferred anywhere, only continues to exist because it happens to be moving in a direction that shouldn't have been the expected outcome of its own formation. Understanding why it ended up that way means asking a harder question than how big the rings are or what's forming inside them. It means asking what kind of object J1407b actually is, and whether the label planet even applies to it in the way we normally use that word. If the ordinary rules of planet formation don't explain the direction these rings move, what does that say about whether J1407b belongs to its star at all? Answering whether J1407b actually belongs to its star means starting with what belonging to a star technically requires. A bound planet follows a closed, roughly stable orbit shaped entirely by its star's gravity, the same way Earth traces the same general path around our Sun year after year. A free-floating object, by contrast, either never formed inside a stellar system in the first place, or formed there and later got flung out entirely, drifting through interstellar space with no star holding it on a fixed track. The retrograde ring instability from earlier doesn't answer that question by itself. It only shows that a stable, gravitationally bound configuration is harder to achieve here than researchers originally assumed. Whether J1407b is bound or drifting is a separate question, and one the data still can't settle cleanly. Free-floating giant planets aren't a hypothetical category invented to explain this one system. Surveys of young star-forming regions have identified dozens of Jupiter mass and larger objects moving through space with no parent star nearby at all, confirmed through direct imaging rather than inference from a light curve. Some of these rogue worlds appear to have formed the same way stars do, condensing directly from a collapsing cloud of gas and dust rather than building up gradually inside a disk around an existing star. Others likely did form inside a young planetary system and got ejected later, ejected being the technical term for what happens when gravitational interactions with a nearby star, or with another massive planet, fling an object onto an unbound trajectory fast enough to escape the system's gravity entirely. That second pathway matters specifically for J1407b, because it connects directly to the instability problem already established in the ring modeling. If a prograde ring configuration genuinely cannot survive this close to J1407's star, one explanation is that J1407b started on a bound prograde orbit and gradually got perturbed onto an unstable path, close enough to the star at some point in its history that gravitational interactions began stripping away orbital energy rather than settling it. Under that scenario, the object we observe today might already be in the process of that separation, no longer cleanly bound in the way a textbook definition of a planet would require, but not yet far enough away to be unambiguously free either. Caught, in effect, mid-transition between two categories astronomers usually treat as distinct. The word planet carries an assumption baked into it that the object in question is gravitationally settled into a lasting relationship with its star. The word rogue carries the opposite assumption that no such relationship exists at all. J1407b's. Ring instability raises a real possibility that neither label fits comfortably, that the object exists somewhere in the physical space between those two definitions, and that forcing it into one category or the other might tell you less about the object itself than about the limits of the vocabulary being used to describe it. Some researchers have pushed further than a bound versus rogue distinction and questioned whether J1407b qualifies as a planet under any definition at all, given how uncertain its mass remains. Early estimates ranged from roughly 2 to as much as 40 Jupiter masses, depending on which model was used, a spread wide enough to place the object comfortably in planetary territory at the low end and well into brown dwarf territory at the high end. That 13 Jupiter mass threshold for deuterium fusion isn't an arbitrary line drawn for convenience. Below it, an object's core never gets hot and dense enough to fuse anything, and it spends its entire existence slowly cooling and radiating away the heat left over from its formation. The same fate every planet in our solar system shares. Above it, brief deuterium fusion ignites in the core for a few million years before fading out, a physical process that planets, by definition, never undergo. J1407b's. Mass uncertainty means it could plausibly sit on either side of a boundary that isn't cosmetic, but describes two genuinely different internal physical processes happening at the center of the object. Narrowing that mass estimate required comparing J1407b against something researchers understood far better: the handful of confirmed brown dwarfs and young giant planets already directly imaged and measured around other stars. Brown dwarfs of a known age and mass follow a fairly predictable pattern of cooling and dimming over time, so comparing J1407b's estimated brightness and temperature against that pattern lets researchers narrow down which mass range is actually consistent with an object this young. Most current estimates now favor the lower end of the original range, likely somewhere between roughly 2 and 14 Jupiter masses, which places J1407b close to that fusion boundary rather than deep inside confirmed brown dwarf territory, but the uncertainty hasn't fully closed, and no measurement to date has pinned the value down with the same confidence astronomers have for planets detected through more direct methods. The temptation in any field is to resolve ambiguity as quickly as possible, to assign a label and move on, because unresolved categories are uncomfortable and headlines prefer certainty. Astronomers working on J1407b have largely resisted that temptation, publishing mass ranges instead of single confident numbers, describing orbital stability as an open modeling question instead of settled fact. That restraint isn't indecision. It's the same discipline visible all the way back at the original 2012 discovery paper, when Mumajek and Pickow described only a cautious disk hypothesis rather than announcing rings outright before the modeling existed to support that claim. J1407b's rings are measured with real precision, more than 30 individual bands extending out to roughly 0.6 astronomical units. That part of the picture holds up under repeated scrutiny. But the object those rings surround still resists a clean answer to three basic questions any introductory description would normally settle immediately: whether it's a planet or a brown dwarf, whether it remains gravitationally bound to its star or is drifting free, whether the moon apparently forming inside its rings will ever finish that process at all. Most objects this well studied have long since had those basic questions closed. J1407b hasn't. And that isn't a gap in the research. It's an honest reflection of how strange this particular system actually is, sitting close enough to several different categories that none of them quite fit. What J1407b can teach us, regardless of what we eventually call it, starts with a question planetary scientists have carried for decades without a real answer. Did Jupiter and Saturn once have ring systems like this? Not the thin, quiet rings we see around them today, but something closer in scale to what surrounds J1407b right now. A wide, structured disk still in the process of building moons. The theoretical case for that idea is old, older than any confirmed evidence to support it. Models of how gas giants form predict that as a young planet pulls in material from the disk surrounding its parent star, some of that material settles into orbit around the planet itself rather than falling directly onto it, forming a smaller circumplanetary disk. That disk, the models predicted, would gradually clump together into moons over a few million years, the same basic process that built Jupiter's 4 largest moons and Saturn's own major satellites. For decades, that prediction had no direct confirmation. Astronomers could point to the finished moons and infer that something like this must have happened, the way you might infer a wildfire happened by looking at a burned forest, but nobody had ever caught the disk itself, mid-formation, doing the actual work. J1407b is close to the first system where that predicted phase is visible directly rather than inferred after the fact. A ring system carrying roughly 1 Earth mass of material, with at least one large gap consistent with an actively forming moon somewhere between the mass of Earth and Mars, matches the theoretical picture of circumplanetary moon formation closely enough that researchers describe this system as a natural laboratory for testing ideas that previously existed only as equations. That phrase, natural laboratory, undersells what it actually means. A laboratory built on Earth lets you control variables and repeat an experiment. This one lets you watch a process that unfolded around Jupiter and Saturn more than 4 billion years ago, happening again, right now, around a star 434 light-years away. Comparing J1407b's rings to Saturn's directly reveals just how much has changed since Saturn's own moons finished forming. Saturn's current rings extend out to roughly 80,000 miles from the planet and contain a small fraction of an Earth mass in material, mostly water ice with only trace amounts of rock and dust. J1407b's rings extend roughly 200 times farther and carry something close to a full Earth mass. That difference in scale isn't a difference in kind. It's a difference in age, or more precisely, a difference in how far each system has progressed through the same basic process. Saturn's rings are what remains after most of the original disk material has already been swept up into moons, leaving behind a comparatively thin remnant. J1407b's rings still hold most of that original material, largely unconsumed, which is exactly why the system looks so much larger and so much more massive by comparison. The Cassini division, the wide gap visible in Saturn's rings from any reasonably powerful backyard telescope, exists because the moon Mimas clears that space through the same gravitational mechanism believed to be carving the gap in J1407b's rings today. Saturn's gap-clearing process finished its major work long ago. Mimas is a fully formed moon now, roughly 250 miles across, not still accumulating material the way the hypothesized moon inside J1407b's rings appears to be. Watching Saturn's finished gap next to J1407b's still active one is close to watching 2 frames of the same film, one taken near the end of the process, one taken somewhere in the middle. If J1407b really does represent an earlier stage of the same process that built Saturn's moons, then somewhere in Saturn's deep past, roughly 4.5 billion years ago, its own rings likely looked far more like what we see around J1407b today than like what we see around Saturn now. Vita, heavier, carved by gaps that hadn't yet finished their work. Saturn's rings as we know them, thin, sparse, comparatively delicate, aren't the planet's original state. They're closer to a late chapter, most of the story already finished. The raw material mostly spent on the moons Saturn now carries instead. Nobody studying this system claims Saturn definitely looked exactly like J1407b's rings do now. The comparison is a model. supported by consistent physics and a matching theoretical framework, not a photograph of Saturn's actual early history. What makes it worth taking seriously isn't certainty. It's that every independent piece of evidence, the gap-clearing mechanism, the moon mass estimates, the total ring material, the age of the host star, points in the same direction rather than contradicting each other. That kind of internal consistency across multiple separate lines of evidence is closer to how confidence actually gets built in science than any single dramatic confirmation could provide. Beyond Saturn specifically, this system reframes a broader assumption about what's rare in the universe and what isn't. Ring systems around gas giants were, until relatively recently, something astronomers assumed we understood mainly from 4 examples: Jupiter, Saturn, Uranus, and Neptune, all studied up close, only because spacecraft eventually visited them directly. J1407b demonstrates that ring systems can exist around planets we'll likely never send a spacecraft to, planets far too distant for anything but light curve modeling to ever reveal their structure. That shifts the open question from whether ring systems like this exist elsewhere to how common they actually are, and how many of them we're simply missing because catching one requires an object to pass directly in front of its star from our specific vantage point at exactly the right moment, while someone happens to be watching closely enough to notice. The odds involved in that alignment are worth naming plainly. For an eclipse like J1407b's 56-day event to be visible from Earth at all, the ring system's orbital plane has to align almost perfectly with our line of sight, a geometric coincidence that isn't guaranteed for any given ringed exoplanet, no matter how large its rings might be. If that alignment happens only rarely across the full population of ringed giant planets in our galaxy, then J1407b likely isn't a rare object in absolute terms. It may simply be one of the rare cases where the geometry lined up well enough for us to catch it happening at all. Every other ring system out there, similarly massive, similarly young, similarly caught mid-formation, could be orbiting stars we've already surveyed, invisible to us purely because its plane never lines up the way J1407b's does. J1407b isn't likely a cosmic anomaly, a single strange exception to how planets and moons usually form. It's more probably a common process, caught for once at exactly the right angle to be seen, revealing a phase of planetary history that likely played out around countless young stars, including our own, long before anyone existed to watch it happen. What we're looking at when we look at J1407b's rings may be less a strange exception and more an ordinary chapter in planetary formation that almost nothing else has let us witness directly, because almost nothing else has happened to line up the way this one system, by chance, finally did. If Saturn's own rings really were once something closer to this, wider, heavier, still actively building moons, then what else about our solar system's early history has already vanished so completely that nothing remains to prove it ever happened at all? What vanished from our solar system's early history left almost no direct trace. A moon stays formed for billions of years, a permanent record of the material that built it. The disk it came from does the opposite. It gets consumed by its own formation process, spent on the very objects that prove it once existed, leaving nothing behind to study directly except the finished result. That's part of why a system like J1407b matters beyond satisfying curiosity about one distant object. It's one of the only places where that consumption process hasn't finished yet, which means it's one of the only places where the vanishing itself is still observable rather than already complete. J1407 sits, roughly 434 light-years from Earth. Light moving at approximately 670 million miles per hour takes that long, 434 years, to cross the distance between that star and any telescope pointed at it from here. A commercial jet flying at roughly 550 miles per hour would need something close to 500,000 years to cover that same distance, meaning even our fastest-built machines fall short of light's pace by a factor of nearly 1,000,000. Every photon reaching a telescope from J1407 tonight left that star before the year 1600, before telescopes themselves had been invented on Earth to eventually receive it. That delay changes what observing actually means for a system like this. The 56-day eclipse recorded by SuperWASP in 2007 wasn't happening in 2007. It happened around the year 1573, and what reached Earth's instruments centuries later was only the light that event produced, arriving on schedule after a journey longer than the entire history of European contact with the Americas. Whatever the ring system and its hypothesized moon are actually doing right now, this instant remains genuinely unknowable to us. We aren't watching J1407b as it currently exists. We're watching a version of it more than 4 centuries old, and the current state of that system won't be visible from Earth until light carrying that information completes its own 434-year crossing. This limitation isn't unique to J1407b. Every distant object astronomers study carries some version of this same delay, a fundamental speed limit built into how information moves through the universe, meaning nothing we observe anywhere beyond our immediate surroundings shows on us the present moment. What changes here is how consequential that delay becomes. Given how much this specific system appears to be actively changing on human-relevant timescales, an exomoon possibly still accreting material, ring gaps possibly still widening, all real physical processes unfolding in real time somewhere out there, invisible to any instrument on Earth until centuries after the fact. Picture standing on the surface of that hypothesized exomoon. Somewhere inside the gap it is carved through J1407b's ring material. The planet itself would dominate the sky from that vantage point, filling a far larger portion of it than any planet visible from any moon in our own solar system, since this hypothesized moon orbits close enough to its parent to complete a full circuit in roughly 2 years, rather than the months or decades typical of moons around Jupiter or Saturn. Above and around that planet, instead of open black sky, would stretch the ring system itself, tens of individual bands extending outward toward a horizon so distant it would blur into the general dimness of surrounding space rather than resolve into any sharp edge. Light reaching that surface wouldn't arrive the way sunlight reaches Earth, unobstructed stream. Depending on where the moon sits relative to the densest ring bands at any given point in its orbit, ring material overhead would filter incoming starlight the way clouds filter sunlight here, sometimes thinning to something closer to full exposure, sometimes thickening into something closer to permanent overcast. Over the roughly 10-year orbital period J1407b itself takes to circle its star, and the roughly 2-year period this hypothesized moon takes to circle J1407b, that overhead lighting would shift slowly and predictably, an atmosphere-free equivalent of long seasons, driven not by axial tilt the way Earth's seasons are, but by orbital geometry relative to a ring structure hundreds of millions of miles across. No such surface has ever been observed. This remains a model built from confirmed physics rather than a confirmed scene, and treating it as anything more than a carefully reasoned possibility would overstate what the evidence actually supports. Human intuition struggles with numbers presented as pure abstraction. A ring system spanning 0.6 astronomical units, meaning very little as a felt experience, until translated into something a body could stand inside. The translation doesn't make the science less rigorous. It makes the rigor legible to a mind built for scale far smaller than interplanetary distances, a mind that evolved to judge distance in footsteps and days, not in light years and astronomical units. That gap between what the universe actually contains and what a human nervous system can directly register runs through every act of this journey so far, Whether the subject was a 56-day light curve too slow for casual notice, a mass estimate too uncertain to fit cleanly into planet or brown dwarf, or a distance too vast for any of our fastest machines to meaningfully close. None of those gaps mean the science is unreliable. They mean the tools built to bridge them, careful modeling, patient inference from indirect evidence, honest uncertainty held for over a decade rather than collapsed prematurely into false confidence, are doing exactly the work they were built to do. Understanding something this distant was never going to feel intuitive. It was only ever going to feel earned, one careful inference at a time, across years of researchers refusing to claim more than the evidence actually supported. If the light reaching us tonight left before the instruments meant to receive it even existed, what does it actually mean to say we've discovered anything about J1407b at all, rather than simply discovered evidence of what it used to be? Discovering evidence of what J1407b used to be, rather than what it is now, raises a practical question underneath the philosophical one. If the light reaching us tonight is already centuries old, is there any way to get closer to the present? Any way to check whether the picture built from that 2007 eclipse still holds? There is, but it depends entirely on something the system itself controls, not on any advance in telescope technology. It depends on J1407b passing in front of its star again. Kenworthy's modeling placed J1407b's orbital period at roughly 10 years, meaning the object completes one full circuit around its star only once per decade. An eclipse is only visible from Earth during the narrow window when the planet and its ring system happen to pass directly between us and the star, so 10 years isn't just how long the orbit takes. It's roughly how long astronomers have to wait between opportunities to gather fresh data on this system at all. The 2007 event was caught essentially by chance, an automated survey recording a data point nobody yet understood the significance of. The next transit was expected sometime in the 2020s, and unlike 2007, this time astronomers would be watching for it deliberately, with instruments and expectations the original survey never had. That shift, from accidental discovery to deliberate anticipation, changes what kind of science becomes possible. A single unexpected eclipse, however well modeled after the fact, only ever produces one version of the story, filtered entirely through whatever instrument happened to be pointed in the right direction at the right time. A second, anticipated eclipse lets researchers point purpose-built monitoring campaigns at the star in advance, gathering far more precise brightness measurements across the full transit than SuperWasp's original wide-field survey was ever designed to capture. It also allows something the first eclipse couldn't offer at all, a direct test of the model itself. If Kenworthy's reconstruction of more than 30 rings, extending to roughly 0.6 astronomical units, correctly predicts the timing and shape of dimming during a future transit, that agreement would confirm the model far more rigorously than fitting it retroactively to data already in hand. Coordinating that kind of watch isn't work that falls only to professional observatories with dedicated funding and staff. Amateur astronomers, people observing from backyard telescopes and small private observatories, have historically played a real role in monitoring predictable but rare events like this, partly because professional telescope time is expensive and heavily oversubscribed, and partly because a network of observers scattered across different longitudes can track an event continuously as the target rotates out of view from any single location. That kind of distributed, collaborative watching has a long history in astronomy, going back to 19th century expeditions that spread observers across continents to catch total solar eclipses from multiple vantage points at once. J1407's decade-long orbital period places it in a similar category, a genuinely rare event worth organizing real effort around, rather than something any single telescope could reliably catch alone. Committing years of attention to a single object, with no guarantee the next transit will even be visible from any given location, given weather, given competing observation schedules, given the basic uncertainty of predicting an orbit, this precisely from a single prior data point takes a specific kind of patience that doesn't show up in most descriptions of scientific discovery. The dramatic version of this story ends in 2012 with a published paper and a named object. The quieter, truer version continues well past that point, into years of researchers checking ephemeris predictions, refining orbital models, and simply waiting for a star 434 light-years away to do, on schedule, the one thing that would let them test everything they'd built. That patience connects directly back to something established earlier in this same story, in a different form. Mark Picot didn't find this system by searching for it specifically. He found it while doing routine cataloging work, willing to look closely at data that wasn't behaving the way it should have. The willingness to wait for a predicted eclipse is the same discipline pointed in a different direction, not searching an archive for an anomaly already recorded, but committing real time and attention toward an event that hasn't happened yet, on the strength of a model built from evidence collected once, years earlier. Both forms of patience share the same underlying commitment. Trusting that careful, unglamorous attention, sustained over years rather than concentrated into a single dramatic moment, is what actually produces reliable knowledge about something this distant and this strange. What a confirmed second eclipse could offer goes beyond simply checking the existing model's math. Comparing two transits separated by roughly a decade would let researchers measure whether the ring system's structure has changed in the intervening years, whether the gap attributed to a forming moon has widened, narrowed, or shifted position, any of which would provide the first direct evidence of the ring system actively evolving on a timescale short enough for humans to observe directly, rather than inferring change only from theoretical models of how such systems ought to behave over millions of years. That kind of direct, before and after comparison doesn't exist yet for any ringed exoplanet, because J1407b remains the only confirmed example. A second data point wouldn't just confirm the first. It would open an entirely new kind of measurement, actual structural change in a planetary ring system, tracked across a single human lifetime rather than reconstructed after the fact from a single frozen snapshot. None of this depends on anything humans need to build or invent. The instruments capable of detecting a second J1407 transit already exist, refined versions of the same wide-field survey technology that caught the first eclipse by accident in 2007. What the confirmation actually depends on is simpler and in some ways harder to control. Whether a star 434 light-years away completes its predicted orbit on schedule, and whether enough patient observers are watching in enough different places when it finally does. That's a strange kind of dependency to sit with honestly. All the modeling, all the careful mass estimates, all the years of restrained, uncertain language in published papers ultimately rests on waiting for the universe itself to confirm or contradict what careful reasoning has already proposed. If the next eclipse arrives exactly where the models predict, precisely on schedule, matching the ring structure reconstructed from a single event recorded almost 2 decades earlier, what would that actually prove about how much can be known from watching shadows alone without ever once seeing the thing itself? Every ring system carries the mechanism of its own ending built into the same physics that lets it exist at all. Ring particles don't simply orbit undisturbed forever. They collide with each other constantly, at low relative speeds compared to their orbital velocity, but often enough over millions of years that those collisions steadily reshape the entire structure. Each collision tends to damp out the small differences in orbital speed and inclination between particles, gradually flattening the ring and nudging material toward whatever larger bodies are already forming within it. That process has a name among planetary scientists: collisional accretion, and it runs in one direction only. Material moves from the diffuse, spread-out ring into the concentrated, solid moon, never the reverse. The gap already carved by the hypothesized exomoon isn't a stable feature that will persist unchanged. It's a boundary that keeps advancing, widening as more ring material gets swept up into the growing moon on one side of it. Current models suggest this process could continue for several million more years before the bulk of the ring material has either been consumed by forming moons or scattered by their combined gravitational influence, at which point the wide, structured system observed today would no longer exist in anything like its current form. Several million years sounds distant, measured against a single human life, but measured against the age of the star itself, only a few million years old, it means this ring system is disappearing on a timescale close to the same order of magnitude as its own age, not a permanent feature of the J1407 system. A phase, already well underway, that started sometime before humans existed and will likely finish sometime after any record of this discovery has been forgotten. That timescale connects directly to something visible much closer to home. Saturn's rings, by contrast, are now understood to be comparatively young themselves, likely no more than a few 100 million years old, far younger than Saturn's own 4.5 billion year history. That conclusion comes from measuring how quickly ring material falls into Saturn's atmosphere under the pull of the planet's magnetic field, a slow rain of ice and dust that gradually depletes the rings from the inside, distinct from the collisional accretion reshaping J1407b's rings, but pointing toward the same underlying truth. Ring systems don't last indefinitely under any known mechanism. Saturn's current rings are themselves a temporary structure, likely to thin out and vanish within the next few 100 million years, meaning the delicate, iconic rings visible through any backyard telescope tonight are not a permanent feature of our solar system either. Just one running on a slower clock than J1407b's. There's a specific kind of vertigo in holding those two timescales side by side. J1407b's rings are disappearing quickly enough that the moon carving through them might finish forming within a span short enough to imagine several million years, roughly the same order of time, separating modern humans from our earliest recognizable ancestors. Saturn's rings are disappearing slowly enough that they'll likely outlast our own species by a significant margin, unless something else ends first. Neither timescale is truly permanent by the standard the universe actually keeps. Both are temporary arrangements, visible now purely because now happens to fall somewhere inside the window where the material hasn't yet finished moving from ring to moon or from ring to planetary atmosphere. That framing changes what it means to have caught J1407b's eclipse at all, back in 2007. A survey camera didn't just record a strange light curve from a distant star. It recorded a specific, narrow moment inside a much longer process, one slice cut from several million years of gradual transformation, arriving at Earth during precisely the few decades when human instruments existed sensitive enough to detect it, and humans existed patient enough to understand what they were looking at. Shift that recording earlier by even a few 100,000 years, still a small fraction of the total process, and the ring system might have looked different enough that the same modeling techniques would have reconstructed a different structure entirely, more material, fewer defined gaps, an earlier stage of the same disappearance already in progress. Mamajek and Picot described only a cautious disk hypothesis in 2012, not because the evidence was weak, but because claiming more than the data supported would have meant treating one narrow snapshot as though it revealed a permanent, unchanging truth about the system. Kenworthy's later modeling extended that same caution into the ring structure itself, describing more than 30 bands and an estimated exomoon mass without ever suggesting the picture was finished or fixed. Understanding now that the entire system is actively dissolving on a timescale of millions of years makes that caution look less like professional restraint and more like an accurate response to what the object actually is. A structure this size, observed this briefly, was never going to hold still long enough to be described with false permanence. Watching Saturn's rings requires no unusual luck. They've persisted for hundreds of millions of years and will likely persist for a few 100 million more, calm and available to anyone who points a telescope at the right patch of sky on almost any given night. Watching J1407b's rings required something considerably rarer. A star 434 light-years away, happening to pass its ring system directly across our line of sight during the same few decades that survey astronomy had matured enough to catch it, and during a phase of that ring system's existence still active enough to have anything worth catching at all. Miss this narrow overlap in cosmic and technological timing, and the same 56 days of dimming light might have arrived at an Earth with no instruments capable of recording it, or might never have happened to cross our sightline in the first place. That overlap, more than any single number describing the ring system's size or mass, is what makes this particular discovery difficult to fully replace. Other ringed exoplanets almost certainly exist elsewhere, hidden from us purely by unfavorable geometry. But each one carries its own narrow window, its own specific stretch of millions of years, during which its rings remain wide enough and active enough to be worth finding, aligned with whatever brief span of time a civilization capable of looking happens to exist nearby. Whether any of those other windows will ever overlap with human observation, the way this one did remains completely unknown. If a structure 200 times larger than Saturn's rings is already disappearing on a timescale this short, what does that say about everything else out there, still forming and still dissolving, that simply never happened to align with a telescope pointed the right way at the right moment to notice it at all? Everything reconstructed so far, the ring width, the gap, the hidden moon, the decade-long orbit, depends on one assumption that has never actually been confirmed: that J1407b is orbiting its star at all, in the ordinary sense that word implies for every other exoplanet ever catalogued. The retrograde ring instability already established that a standard-bound orbit close to this star struggles to keep the ring system intact. What it didn't settle is whether the planet itself remains gravitationally tied to that star in any conventional way, or whether the object we call J1407b might not belong to a stellar system at all. Free-floating planets are not a fringe idea invented to rescue this one system from an awkward result. Surveys of young star-forming regions across the galaxy have directly imaged dozens of objects with masses in the range of several Jupiters, moving through space with no host star detectable anywhere near them. Some of these appear to have formed the way stars form, condensing directly out of a collapsing cloud of gas rather than accumulating gradually inside a disk around an already existing star. Others almost certainly formed inside a young planetary system first, then got ejected later, flung onto an unbound trajectory by close gravitational encounters with a sibling planet or a passing star, fast enough to escape the pull that once held them in place. Both origin stories produce the same end result: an object massive enough to be called a planet, moving through interstellar space with no star to call its own. That second pathway, ejection after formation, connects directly to what the ring modeling already revealed. If a ring system this size genuinely cannot survive for long on a standard prograde orbit this close to a star, one explanation is that J1407b began its life closer to a conventional bound orbit and has since been perturbed onto a path that no longer holds. Gravitational interactions strong enough to destabilize an orbit don't have to happen instantly. They can unfold gradually, over millions of years, as small deviations compound into larger ones, the same way a coin balanced on its edge doesn't fall the instant it's disturbed, but tips further with each passing moment until the fall becomes unavoidable in hindsight, even if it looked stable for a long stretch beforehand. Under that scenario, J1407b might not be cleanly bound or cleanly free right now. It might be caught somewhere in the process of separating from its star, still close enough for the two to appear associated in the data we have, but already on a trajectory that ends, eventually, with the two drifting apart permanently. That's a genuinely uncomfortable position for a classification system built on clean categories. Astronomers are used to sorting objects into bound or unbound, planet or brown dwarf, and J1407b keeps landing in the seam between categories rather than settling cleanly into one side. A planet, by the definition most astronomers use, is an object that formed within a disk around a star and remains gravitationally dominated by that star's orbit. Strip away the second half of that definition, and you're left with something that formed like a planet but no longer behaves like one, an object whose history and current state have diverged from each other. Language built for tidy categories runs into trouble here, not because the physics is unclear, but because the physics describes a transition, and transitions don't sit still long enough for a single label to describe them accurately at every point along the way. Some researchers have pushed this even further, questioning whether the bound or rogue distinction is the right frame at all for an object whose mass estimate still ranges from roughly 2 to as much as 40 times Jupiter's mass, depending on the model. At the low end of that range, J1407b behaves like an unusually large planet. At the high end, it edges into brown dwarf territory, an object massive enough to briefly fuse deuterium in its core for a few million years before that fusion sputters out, a process no true planet ever undergoes. A brown dwarf drifting freely through space isn't unusual or theoretically troubling in the way a free-floating true planet is. Brown dwarfs often form in isolation to begin with, the same way small stars do, condensing directly from a collapsing cloud rather than requiring a parent star's disk to build them. If J1407b sits toward the high end of its mass range, the free-floating explanation stops being a strange exception and starts looking like an entirely ordinary outcome for an object of that type. Narrowing that mass estimate has required comparing J1407b against the small number of directly imaged brown dwarfs and giant planets around other young stars, objects whose brightness and temperature can be measured directly rather than inferred only from a light curve. Young substellar objects cool and dim in a fairly predictable pattern as they age. So matching J1407b's estimated brightness against that cooling curve lets researchers narrow the plausible mass range. Most current estimates now cluster toward the lower half of the original spread, likely somewhere between roughly 2 and 14 Jupiter masses, closer to the planet side of the fusion boundary than the brown dwarf side, though the uncertainty has never fully closed, and no single measurement has pinned the number down with the same confidence astronomers have for planets found through more direct detection methods like radial velocity or direct transit timing. A light curve reveals how much starlight something blocked and for how long. It cannot directly weigh the object doing the blocking. Every mass estimate for J1407b comes from indirect reasoning, comparing its brightness and inferred temperature against a library of better understood objects, then working backward toward a range rather than a fixed number. That indirection isn't a weakness unique to this system. It's the condition under which almost everything about J1407b has been learned, one careful inference stacked on another, each one narrowing the range of what's possible without ever quite arriving at certainty. Every time researchers push one layer of this system into sharper focus, ring width, gap mass, orbital direction, the sharper focus reveals a deeper layer of uncertainty rather than resolving into a final answer. That isn't a failure of the science. It's closer to what happens when you study something genuinely caught between two familiar categories, close enough to each to resemble both, distant enough from either to fully commit. If J1407b really is somewhere in the process of drifting free of its star, gradually losing whatever gravitational hold once kept it bound, what happens to a ring system and a forming moon when the star providing part of their gravitational context simply stops being close enough to matter? If J1407b really is drifting free of its star, gradually losing whatever gravitational hold once kept the two connected. The first thing to understand is what that separation would and wouldn't change about the ring system itself. Losing stellar gravity doesn't mean losing all gravity. The planet's own pull, whatever its exact mass turns out to be, still holds the rings and the forming moon in place around it, the same way Jupiter's moons stay bound to Jupiter regardless of how far Jupiter sits from the Sunday. What changes is only the second gravitational influence, the star's competing pull that made a stable prograde orbit so difficult to sustain in the first place. Remove that competing pull entirely, and the physics governing the rings actually simplifies rather than complicates. That simplification matters directly for the moon formation process already underway. The instability calculated for a prograde ring orbit close to the star assumed the star's gravity was actively working against the ring system's own rotational momentum, stripping material away over time. A fully free-floating J1407b, with no nearby star exerting that competing pull, wouldn't face the same constraint. Under that scenario, the rings could persist in whatever orientation they already occupy, prograde or retrograde, without the earlier instability calculation applying at all, since that calculation depended entirely on the star's proximity as the destabilizing force. Free-floating, ironically, might turn out to be the condition under which this ring system's continued existence makes the most physical sense. This is where the two competing explanations from earlier in this account stop looking like separate possibilities and start looking like two chapters of the same story. One describes a snapshot of the ring system's current orbital geometry. The other describes a longer history that could explain why that geometry ended up so unusual in the first place. If J1407b formed inside a young planetary system, then got ejected through gravitational interactions with a sibling planet, that ejection process wouldn't have preserved the original, simple orbital alignment the planet started with. Ejection is chaotic by nature, and a chaotic departure from a stellar system could easily leave a planet's surrounding rings in whatever tilted, retrograde, or otherwise unusual configuration happened to result from that specific gravitational encounter. None of this has been confirmed. Distinguishing a bound planet on an extremely wide, slow orbit from a genuinely free-floating object requires measuring the object's actual trajectory across the sky over years, tracking whether it's following any curved path consistent with orbiting a star, or moving in a straight line consistent with drifting freely through space. That kind of precise position tracking, called astrometry, requires either extremely long observational baselines or instruments sensitive enough to detect proper motion, this subtle at a distance of 434 light-years. Neither has yet produced a definitive answer for J1407b specifically, which means the free-floating hypothesis remains a genuine possibility supported by circumstantial evidence, not a settled conclusion. Nearly every major finding in this system's story has followed the same shape. A measurement gets made. That measurement raises a question the original data can't fully answer. Answering it requires either new data that doesn't yet exist or new instruments not yet pointed in the right direction. The ring width came from light curve modeling, which couldn't determine ring composition. The exomoon mass came from gap analysis, which couldn't confirm the moon's actual existence through direct detection. The orbital orientation came from stability modeling, which couldn't determine whether the underlying cause was an unusual retrograde configuration or a planet already drifting free. Each answer opened exactly one new unanswered question in a chain that has run continuously since 2007 and hasn't yet reached its end. That chain represents something researchers rarely get to see laid out this clearly. Most confirmed exoplanets have known masses, known orbital periods, with the second's compositions inferred with reasonable confidence. J1407b still carries open questions at the most basic level, whether it's a planet or a brown dwarf, whether it's bound to a star or drifting free, whether the moon apparently forming in its rings actually exists as a solid body or merely as a gravitational influence too diffuse to have consolidated yet. Sitting with that level of persistent uncertainty, more than a decade after the original discovery, requires a specific kind of comfort with not knowing, one that runs directly against the instinct most people have when encountering an unfamiliar object for the first time, the instinct to reach for a label and move on. The astronomers who've worked on this system, from Picot's initial catalog check through Mamajek's cautious 2012 paper to Kenworthy's detailed ring modeling years later, have consistently resisted that instinct. Each of them, at each stage, published exactly what the evidence supported, and no more, leaving room for the next researcher, with better data or a sharper model, to push the picture further without having to first correct an overstated earlier claim. That's a specific kind of professional integrity, choosing to publish an honest, incomplete picture over a tidy, premature one, and it's part of why this system's story has held up so well under more than a decade of continued scrutiny, rather than collapsing the way overstated early claims often do, once better instruments arrive. What all of this leaves is a working list of genuinely unresolved questions rather than a finished description. Whether J1407b's mass sits closer to 2 Jupiter masses or closer to 14, whether it remains gravitationally bound to its star or has already begun drifting free, whether the exomoon inferred from the ring gap is a solid, coherent body or still a diffuse concentration of material not yet consolidated, whether the rings orbit retrograde because of an unusual formation history or because the entire system is in the process of separating from its star. None of those questions has an answer yet. All of them depend on future data, most likely the next transit, whenever it arrives, carrying whatever new information a decade of continued drift and accretion has added to the picture since the last time anyone was able to look. If every answer this system has produced so far has opened exactly one new question in its place, what does that pattern suggest about whether a complete, settled understanding of J1407b is even the right thing to expect, or whether some objects simply stay this way, genuinely unresolved, for as long as anyone keeps looking? Every open question raised so far, the mass, the orbital status, the moon's exact composition, depends on one underlying fact that changed the day this discovery became public. Before 2012, nobody was systematically looking for ring systems around other stars, because nobody had confirmed one existed to look for. After Kenworthy's modeling paper appeared, that changed. Astronomers now had a specific signature to search for, a long, structured, multi-day dimming event with rapid internal flickering, and a method already proven capable of reconstructing real physical detail from nothing but a light curve. That shift from theory to method matters more than it might sound at first. A theoretical prediction tells you something should be possible. A confirmed detection tells you exactly what to look for and how to recognize it when it appears. Before J1407b, the search for exoplanet rings existed only as an idea buried inside broader planet formation models, something astronomers assumed must exist somewhere but had no concrete search strategy for finding. After J1407b, that search had a template. Astronomers could go back through archived survey data from missions never designed to look for rings and search specifically for light curves with this exact signature: long duration paired with fine internal structure, the same combination Picot happened to notice by chance in 2010. Searching archived data this way is fundamentally different from searching in real time. Wide-field surveys like SuperWASP and its successors generate enormous volumes of brightness measurements every single night, far more than any team of researchers could review individually as it comes in. Most of that data gets processed by automated systems built to flag specific, expected patterns, the short, clean transit dips typical of ordinary planets. A signal shaped like J1407b's would have been filed and ignored by most of those systems, exactly as it was the first time, unless someone specifically built a new search algorithm designed to recognize this particular, unusual shape. That's precisely what happened after 2012. Researchers wrote new detection algorithms trained specifically on the confirmed signature from J1407b, then applied those algorithms retroactively to years of archived survey data that had already been collected and set aside. That retroactive search has produced candidates, though none yet confirmed with the same confidence as J1407b itself. A handful of other young stars have shown brightness dips with some of the same characteristics: long duration, internal structure suggesting a layered rather than solid occulting object, but confirming any of them as a true ringed exoplanet requires the same painstaking modeling work Kenworthy applied here, testing ring configurations against the observed data until one reproduces the fine detail correctly. That process takes years for a single candidate. It isn't a search that scales quickly, which is part of why, more than a decade after the original discovery, J1407b remains the only ring system outside our solar system confirmed with this level of physical detail. There's a specific kind of humility built into that slow pace. Finding a candidate signal in archived data is the easy part now, since the search algorithms exist and the pattern is known. Confirming that signal as an actual ring system with a specific radius, a specific mass, specific internal structure requires the same years-long modeling discipline that took Kenworthy's team from a 2012 disk hypothesis to a fully reconstructed ring system years later. Every candidate found since has had to earn that same level of scrutiny before being taken seriously, and most candidates don't survive it. A light curve that looks superficially similar to J1407b's under casual inspection often fails to match under detailed modeling, revealed instead to be an eclipsing binary star, a background contamination artifact, or simply noise that happened to cluster in a suggestive pattern. That failure rate isn't a weakness in the search method. It's exactly what a rigorous method should produce. If every candidate signal turned out to be a confirmed ring system, that would actually be a warning sign, evidence that the confirmation standard had grown too loose to filter out false positives. The fact that J1407b still stands largely alone, more than a decade after its discovery, despite active searching using algorithms built specifically to find more examples like it, tells researchers something real about how rare this particular alignment of circumstances. A young star, a ring system still wide enough to matter, and an orbital geometry that happens to cross our line of sight actually is. This connects back to something established earlier about the geometric luck required for any single ring system to be visible from Earth at all. For any given ringed exoplanet, however common such systems might turn out to be across the galaxy, the odds that its orbital plane happens to align closely enough with our specific vantage point to produce a visible eclipse are low. That means the true rarity being measured by this slow, difficult search isn't necessarily the rarity of ring systems themselves. It may be measuring the rarity of favorable alignment, a separate question the search method can't yet distinguish from actual physical scarcity. Every year without a second confirmed detection adds weight to one interpretation or the other, without yet settling which one is correct. What all of this represents, taken together, is a scientific legacy that extends well past the specific facts learned about one distant object. J1407b didn't just answer a question about whether ring systems exist outside our solar system. It created an entire methodology, a search technique, a confirmation standard, and a growing body of researchers now actively applying both to archived and future survey data, purely because one graduate student happened to look closely at an unusual chart in 2010. That's a specific kind of scientific inheritance, harder to quantify than a single discovery, but arguably more consequential, the difference between finding one answer and building the tool that lets an entire field keep asking the same question more precisely, again and again, for as long as anyone keeps looking. If the search techniques built directly from this one discovery eventually confirm a second ringed exoplanet somewhere else in the galaxy, what would that tell us about whether J1407b was ever truly unique, or whether it was simply the first system patient enough and lucky enough in its alignment to let us notice what may turn out to be an entirely ordinary feature of how young planets grow their moons? Whether J1407b turns out to be unique or simply the first of many depends on a distinction. Astronomers rarely get to draw this cleanly. A phenomenon can be rare in the universe, or rare in what we've managed to observe, and those are two entirely different claims dressed up in the same sentence. J1407b has stood alone for more than a decade, but standing alone in our data isn't the same as standing alone in reality. Confusing the two is one of the oldest mistakes in observational science, and it's worth separating carefully before asking what else remains unresolved about this specific object. Start with what we can say confidently, because that list is shorter than most descriptions of this system suggest. The ring system's outer radius, roughly 0.6 astronomical units, trying to delism, comes from modeling that reproduced the 56-day light curve in fine detail, matching not just the overall shape of the dimming, but the rapid internal flickers caused by individual ring bands. That level of agreement between model and observation gives real confidence. When a physical structure built from first principles reproduces minute-by-minute variation across nearly 2 months of data, that isn't a loose fit dressed up as certainty. It's the kind of match that survives scrutiny. Everything built on top of that solid foundation gets progressively less certain. The total ring mass, estimated at roughly 1 Earth mass, comes from a chain of assumptions about particle density and composition that the light curve alone can't confirm directly. Change those assumptions within a reasonable range, and the mass estimate shifts with them. The hypothesized exomoon sits one layer further out on that same chain. Its existence is inferred from a gap. Its mass is inferred from that gap's width, and its 2-year orbital period is inferred from applying standard orbital mechanics to a distance that itself depends on the ring model being correct. Each inference is reasonable. None of them is a direct measurement, and stacking reasonable inferences on top of each other doesn't produce the same confidence as a single direct one. This is where a metaphor earns its place, because the abstract idea of stacked uncertainty is easier to hold once it has a physical shape. Picture estimating the weight of a person standing on a scale inside a moving elevator, where you can't read the scale directly but can only measure how much the elevator's own motion changes based on their weight. You could get a reasonable estimate that way, accounting for the elevator's mechanics and how it responds to different loads. But every assumption about the elevator's mechanism adds a small amount of uncertainty to your final number. Uncertainty that compounds the more steps stand between what you actually measured and what you're trying to determine. That's the situation with J1407b's exomoon. Nobody weighed it directly. Its mass comes from a chain of physical reasoning applied to a gap in a ring, and each link in that chain, however sound, adds its own small margin of doubt to the final estimate. None of that uncertainty is a flaw in the science. It's an honest description of what indirect detection can and cannot deliver, and stating it plainly protects the credibility of everything that has been established with more confidence. Compare this to how confirmed exoplanets get detected through other methods. Radial velocity measurements track a star's own slight wobble caused by an orbiting planet's gravity, giving a direct measurement of the planet's mass through Newtonian mechanics applied to observed motion. Direct imaging, on the rare occasions it's possible, actually photographs a planet's light, letting researchers measure its brightness and temperature, without inference, layered on inference. J1407b's ring system was detected by neither method. Everything about it comes from reading shadows in starlight and working backward, which makes it one of the most indirect confirmed discoveries in exoplanet science and also one of the most carefully reasoned, precisely because indirection demands more caution at every step. That caution explains something about how this particular story has unfolded compared to other high-profile astronomical announcements. Plenty of discoveries get announced with confident, simple headlines, then quietly revised or retracted once better data arrives. J1407b's story has moved in the opposite direction. The 2012 paper described a cautious disk hypothesis. Kenworthy's later modeling firmed up the ring structure specifically while leaving mass, composition, and orbital status openly uncertain. More than a decade later, the uncertain parts are still uncertain, not because nobody has tried to resolve them, but because resolving them genuinely requires new data, most likely a second confirmed transit that simply hasn't arrived yet. The story hasn't been walked back. It's been built forward carefully, adding detail only where the evidence actually supported it. There's a specific kind of respect embedded in that pattern. Every time a researcher working on this system had the option to round an estimate up towards something more dramatic, a firmer mass number, a more confident orbital classification, a definite yes on the exomoon's existence, the published record shows them declining that option in favor of the honest range instead. That's a form of respect for the people who would eventually read the paper, trusting them to handle real uncertainty rather than needing a false certainty smoothed over the gaps. It's the same respect this account has tried to extend to you across every act so far, treating an open question as something worth sitting inside rather than something that needs a tidy answer manufactured to close it. Gathering everything unresolved into one place makes the shape of what remains genuinely unknown easier to hold. Whether J1407b's mass sits closer to the planetary end of its range or edges into brown dwarf territory, whether the object remains gravitationally bound to its star or has already begun drifting free, carried loose by whatever gravitational encounter first destabilized its orbit, whether the exomoon inferred from the ring gap exists as an actual consolidated body, or whether that gap reflects a still diffuse concentration of material that hasn't finished collapsing into anything solid yet, whether the ring's unusual orientation reflects an ordinary formation quirk or the lingering signature of a planet in the process of leaving its stellar system behind entirely. None of those four questions has an answer that current data can settle. All four depend on future observation, most likely the next transit, whenever the orbit brings one, carrying whatever fresh information more than a decade of continued drift and accretion has added since the last time anyone was able to look closely. If the most honest description of this system, after everything learned so far, is still a list of open questions rather than a finished portrait, what does that actually say about how much confidence we should place in anything we currently believe about objects this far away, this faint, and this fundamentally strange? Every list of open questions gathered so far points toward the same practical bottleneck. Answering any of them, the mass, the orbital status, the exomoon's true nature, requires new data, and new data for this specific system means waiting for J1407b to cross in front of its star again. That wait has a defined length. Kenworthy's modeling placed the orbital period at roughly 10 years, which means the entire research community studying this object has spent the years since 2012 doing something unusual for modern astronomy, preparing for an event on a calendar rather than analyzing data already in hand. Predicting exactly when that next transit will occur is harder than the 10-year figure makes it sound. The original 2007 eclipse gives one data point marking when the ring system last crossed the line of sight between J1407 and Earth. Projecting forward 10 years gives a rough window, but the precision of that projection depends entirely on how accurately the orbital period itself has been measured, and a single observed transit can only constrain that period loosely. Small uncertainties in the orbital period compound over each full orbit, the same way a slightly imprecise stopwatch drifts further from the correct time the longer you let it run. A 10-year period known only to within a few percent could shift the predicted transit window by months, which matters enormously for anyone trying to schedule a specific night or a specific season of dedicated telescope time. That uncertainty is exactly why this search has depended so heavily on distributed observation rather than a single instrument watching continuously. No observatory, however well-funded, keeps a telescope pointed at one obscure star for years on the chance that a predicted eclipse might begin on any given night within an uncertain multi-month window. Professional telescope time is scheduled competitively, months in advance, and a low-confidence prediction doesn't win the argument for locking down that kind of continuous access. What actually works instead is a wider net. Professional survey telescopes already scanning large sections of sky as part of their normal operations, combined with a network of amateur observers checking J1407b's brightness periodically, watching for the earliest signs that a new dimming event has begun. Amateur astronomers occupy a specific and genuinely important role in this kind of long-term monitoring. A backyard telescope with a basic photometer, an instrument that measures a star's brightness precisely, can track J1407b's light output over months at a fraction of the cost of professional observing time. Scattered across different countries and time zones, a network of amateur observers can watch continuously as Earth rotates, handing off observation from one longitude to the next as night falls in different places, something no single professional observatory tied to one location can do alone. This isn't a lesser version of real astronomy. It's a different structure entirely, built for exactly the kind of patient, distributed watching a rare, long-period event like this requires. There's a historical precedent for this kind of collaborative watching that predates modern astronomy by more than a century, and understanding it clarifies why this approach still works today. 19th century astronomers coordinating observations of total solar eclipses faced the same basic problem, an event visible only briefly from a narrow path across Earth's surface, worth capturing from multiple vantage points to gather as much data as possible before it ended. Expeditions were organized across continents specifically to place observers along that narrow path, each one contributing a slightly different angle on the same brief event. J1407b's transit isn't geographically narrow, the way a solar eclipse is, since it can be observed from anywhere Earth's night side faces the right direction. But the underlying principle holds. More eyes, in more places, watching during the predicted window means a far higher chance that someone catches the transit's actual beginning rather than only its later stages. Catching the beginning matters specifically because of what the original 2007 data revealed about the ring structure. The rapid flickering embedded within the slower 56-day fade carried the fine detail that let Kenworthy's team reconstruct more than 30 individual rings. Missing the earliest portion of a new transit risks missing exactly the part of the ring system that crosses the star's disk first, whatever that portion happens to reveal about how the structure has changed since the last observation. A transit caught only partway through still provides useful data, but a transit caught from its very first moment of dimming provides the complete picture, the entire ring system structure mapped from edge to edge rather than reconstructed from an incomplete slice. This is where the years of patient, in a different form entirely. Mark Pecott found the original signal by looking closely at data nobody else had prioritized, willing to sit with an anomaly rather than dismiss it. The astronomers and amateur observers watching for the next transit are applying that same willingness in reverse, sitting with years of ordinary, unremarkable brightness measurements, night after night, on the chance that one of those nights finally shows the beginning of the pattern they've been waiting a decade to see again. Both forms of patience share the same underlying commitment, that careful, sustained attention, applied without the guarantee of a payoff, is what actually produces reliable knowledge about something this distant and this rare. What a confirmed second transit would ultimately offer goes beyond simply validating the existing ring model, though that validation alone would carry real weight. Comparing two eclipses separated by roughly a decade would let researchers check whether the ring structure has visibly changed in the years between them, whether the gap attributed to the forming exomoon has widened as more material accretes onto it, whether the total ring mass has decreased as collisional processes continue consuming the disk. That kind of direct before and after comparison has never existed for any ringed exoplanet, because no other example has been confirmed with enough precision to support it. A second transit wouldn't just confirm what the first one suggested. It would open an entirely new kind of measurement, active structural change in a planetary ring system, tracked across a span short enough for the same researchers who modeled the first eclipse to still be working when the second one finally arrives. None of this depends on any technology that doesn't already exist. The instruments capable of detecting and precisely measuring a second J1407 transit are refinements of the same survey technology that caught the first one essentially by accident in 2007. What the confirmation still depends on is something no instrument can control. Whether a star 434 light-years away completes its predicted orbit close enough to the calculated window, and whether enough patient observers happen to be watching, in enough different places, during the specific stretch of nights when it finally does. That's an unusual kind of dependency to sit with, honestly. All the careful ring modeling, all the years of restrained, uncertain published language, ultimately rests on waiting for the universe itself to confirm or revise what patient reasoning has already proposed, on a timeline no research grant or funding cycle can accelerate. If the next transit arrives close to where the models predict, and the ring structure it reveals has visibly shifted since 2007, what would that tell us about how much a single distant object can teach us about its own future, simply by giving us the patience to wait long enough to watch it happen twice? Every transit prediction discussed so far assumes the ring system stays roughly where it is until the next eclipse arrives. That assumption deserves a closer look, because giant planets and their surrounding material don't always stay put over the long run, and the reason they sometimes move reveals something directly relevant to a place far closer to home than J1407. Planetary scientists studying our own solar system's early history built a model describing exactly this kind of large-scale rearrangement. Named after the French town where much of the founding work was done, the model proposes that Jupiter, Saturn, Uranus, and Neptune didn't form in their current positions at all. They formed closer together, then gradually migrated outward over tens of millions of years as they exchanged gravitational momentum with a surrounding disk of leftover debris, the same kind of material that once built their moons and, in some cases, their rings. As Jupiter and Saturn shifted position relative to each other, their combined gravity swept through the debris disk like a hand dragged through loose sand, scattering material in every direction rather than letting it settle calmly into stable orbits. Some of that scattered debris got flung outward, eventually forming the Kuiper Belt, the icy region beyond Neptune still populated by countless small bodies today. Other material got thrown inward, toward the young rocky planets still forming closer to the Sun, including Earth. That inward scattering connects directly to a period in Earth's own history known as the Late Heavy Bombardment, evidenced today by the dense clustering of large craters on the Moon's surface, craters that all date to roughly the same narrow window of time, rather than spreading evenly across the Moon's entire history. If the giant planets hadn't migrated, stirring up that reservoir of debris, this bombardment likely wouldn't have happened, or would have looked completely different. That same bombardment also delivered material. Comets and water-rich asteroids, scattered inward by exactly this kind of gravitational disruption, are now considered a serious candidate for how Earth acquired much of its surface water, arriving relatively late in the planet's formation rather than being present from the very beginning. The chaos that cratered the Moon may be part of the same process that filled Earth's oceans. Two outcomes from a single mechanism, one destructive and one foundational, arriving together because they came from the same source. This reframes what a ring and disk system like J1407b's actually represents when placed inside the broader arc of planetary history. It isn't just raw material waiting to become moons around one specific planet. It's the kind of debris reservoir that, given the right gravitational disturbance, could just as easily get flung outward into a wider system, seeding smaller bodies across enormous distances, or thrown inward toward whatever rocky worlds happen to be forming closer to the star. J1407b's rings aren't a closed system building only its own moons. They're a potential source of material for an entire planetary system if J1407b ever experiences the kind of gravitational disruption our own giant planets underwent billions of years ago. Whether J1407b will ever undergo that kind of migration is impossible to answer with current data, and stating that limitation clearly matters more than reaching for a satisfying conclusion the evidence doesn't support. The NICE model for our own solar system was built from multiple, mutually reinforcing lines of evidence: the crater record on the Moon, the current orbital structure of the outer planets, the composition of the Kuiper belt, all pointing toward the same underlying history. Nothing comparable exists yet for J1407, a system too young and too far away to have left behind the kind of long-term orbital and cratering record that lets scientists reconstruct our own solar system's migration story in such detail. J1407b sits in roughly the same formative stage. Our own giant planets likely passed through before their migration began, a young system with a massive circumplanetary disk still actively building moons, not yet settled into whatever final configuration it will eventually reach. If something in J1407's system, a passing star, an unstable orbital resonance with a sibling planet not yet discovered, ever triggers a comparable rearrangement, the debris currently forming J1407b's exomoon could just as easily end up scattered across an entire system that doesn't exist yet in any form we could currently detect. There's a specific kind of perspective shift available here. Every account of J1407b's rings so far has treated them as a self-contained story, a planet, its rings, a forming moon, contained entirely within one system's boundaries. The late heavy bombardment record on the Moon suggests that boundary is more permeable than it first appears. Material that begins as one planet's ring system doesn't necessarily stay that planet's material forever. Under the right gravitational conditions, it becomes raw material for an entire system's later history, arriving at destinations its original planet never directly touched. Some of the water currently in Earth's oceans, water inside human bodies right now, this instant, likely arrived by exactly this mechanism, scattered inward from a giant planet's debris disk during a period of gravitational chaos 4 billion years ago. The connection between J1407b's forming moon and a glass of water on a nightstand isn't a metaphor built for effect. It's the same physical process, witnessed at two different stages, separated by 4 billion years and 434 light-years, but governed by the same basic mechanics of gravity redistributing material across a young, still settling system. If material this far from Earth follows the same rules that once redistributed water and debris across our own solar system billions of years ago, how much of what makes a planet, or a person, standing here now, actually originated somewhere else entirely, scattered inward by a disruption no one alive was present to witness? If material this old and this indifferent to distance can still end up circulating through a human body, the scientists studying it deserve equal attention to the ones who found it. Their names surface only briefly in most accounts of this discovery: a graduate student, a professor, a modeler at a foreign observatory, and then the story moves on to the numbers. The years those names represent deserve a closer look before this journey moves anywhere else. Mark Picot was not searching for rings when he opened J1407's light curve in 2010. He was doing the kind of work that rarely makes it into any published headline, checking stellar ages for a catalog, cross-referencing brightness data other astronomers had already collected and moved past. That work depends on a specific discipline most people never get asked to practice, staying alert to something wrong inside data that looks routine on the surface. Most anomalies in a dataset this size turn out to be instrument error, a bad pixel, a cosmic ray strike, nothing worth a second look. Recognizing the rare case that isn't error, that's actually signal, requires holding two contradictory instincts at once. Skepticism toward the strange thing you're looking at, and enough curiosity to keep looking anyway, instead of dismissing it and moving to the next star on the list. Eric Mamajek carried that same discipline into how the 2012 paper described what they'd found. He had built a career studying young stars and their surroundings, work that trains a specific kind of patience, because young stellar systems change slowly enough that meaningful conclusions require years of accumulated observation rather than a single dramatic measurement. When faced with a signal this strange, the temptation to announce something definitive would have been real. A confirmed ring system around an exoplanet would have made a much bigger headline than a cautious hypothesis about a possible circumplanetary disk. Mamajek's team chose the second option anyway, not because the evidence was weak, but because the evidence available at that point genuinely couldn't support anything stronger, and claiming otherwise would have meant trading accuracy for attention. That choice cost them something real in the short term. Careful language doesn't travel the way bold claims do. A paper describing a possible disk around a possible young giant planet or brown dwarf generates far less immediate excitement than a paper announcing the first rings ever confirmed outside our solar system. The second version, the confident one, wasn't available to them yet, because the modeling that would eventually support it hadn't been done. Choosing the accurate, less exciting version anyway is a decision that only pays off years later, when someone else's careful follow-up work vindicates the caution rather than exposing it as an overcorrection. That follow-up came from Matthew Kenworthy at Leiden Observatory. Working through years of computational modeling, most of the public discussion around this discovery skips entirely. Reconstructing more than 30 rings from a single light curve isn't a task completed in an afternoon. It requires testing an enormous range of possible ring configurations against the observed data, adjusting width, density, and spacing repeatedly until the model's predicted dimming pattern matches what SuperWASP actually recorded across those 56 days in 2007. Each adjustment means running the model again, comparing the output against real data, and refining further. That process, run enough times to arrive at a configuration matching the data's fine detail, represents months or years of a researcher's working life spent almost entirely out of public view. There's a specific kind of respect worth extending to that invisible labor. Finding something strange in a light curve takes attention and a willingness to look closely. Turning that strangeness into a physical model precise enough to trust takes something closer to craftsmanship, repetitive work of testing and adjusting until a model earns the confidence to be published. Kenworthy's own description of the process carries the specific enthusiasm of someone who spent real time inside that data, coming to know its texture the way a craftsman comes to know the grain of a material they've worked for years. None of these three researchers set out to become known for this particular discovery. Picot's primary work involved stellar age catalogs, not exoplanet rings. Mamajek's broader career spans dozens of papers on young stellar systems, of which J1407b represents one notable chapter among many. Kenworthy's research extends well beyond this one system into broader questions about exoplanet detection and characterization. J1407b became significant to each of them, not because they were hunting for exactly this kind of finding, but because each one, at their specific stage of the work, chose to take an anomaly seriously rather than let it pass. That pattern, choosing to take the anomaly seriously, repeats often enough across the history of science that it's worth naming as something closer to a shared discipline than individual brilliance. Anomalies appear constantly in scientific data. Most of them genuinely are noise, error, contamination, nothing worth pursuing. The difference between a career spent chasing false signals and a career that occasionally produces something like J1407b isn't the ability to spot strangeness. Strangeness is easy to spot. It's the judgment to know which strangeness deserves months or years of careful follow-up, and the discipline to actually commit that time once the judgment says yes. More than a decade after the original discovery, none of these researchers has claimed the story is finished. Published follow-up work continues to describe mass ranges rather than fixed numbers, orbital stability as an open modeling question, the exomoon's existence as strongly suggested rather than confirmed. That ongoing restraint, sustained across more than a decade in multiple separate research groups, isn't indecision. It's the same discipline that shaped the original 2012 paper, applied consistently long after the initial excitement of discovery has faded into the slower, quieter work of getting the details right. What that consistency actually represents is something closer to a form of care than a methodology. Care for the object being studied, refusing to flatten its genuine complexity into a simpler story than the evidence supports. Care for whoever reads the published work next, trusting them with real uncertainty rather than a false confidence built to satisfy curiosity quickly. And, in a way easy to overlook, care extended forward across time itself, toward a version of this same research community years from now, checking the next transit against a model built carefully enough to still be worth testing. Every discovery described so far has treated distance as an obstacle to overcome. There's another way to look at that same distance, one that has nothing to do with technique and everything to do with what it means for a species to spend real time, real careers, and real institutional resources understanding a place none of us will ever visit. Start with the plain fact of it. J1407b sits roughly 434 light-years away. No spacecraft built with current propulsion technology could reach it within any human lifetime, or within the lifetime of any civilization likely to exist in recognizable form by the time such a journey finished. Voyager 1, humanity's most distant functioning spacecraft, has been traveling for nearly 50 years and hasn't yet covered even 1,000th of that distance. At its current speed, reaching J1407 would take longer than the entire span of recorded human history repeated many times over. This isn't a place we're preparing to explore. It's a place we've decided to understand anyway, fully aware that understanding is the only form of contact we'll ever have with it. That distinction matters more than it might first appear. Most exploration throughout human history has carried an implicit promise of eventual arrival. Sailors crossed oceans toward coastlines someone would eventually walk on. Early astronomers charted the moon and planets partly because spaceflight, however distant, remained at least theoretically possible. J1407b breaks that pattern entirely. The astronomers who spent years modeling its rings knew, from the outset, that no one would ever confirm their model by sending an instrument there directly. Every conclusion had to stand entirely on inference, because direct verification was never going to be an option, not in 10 years, not in 10,000. Most funding arguments for astronomy lean on practical benefits, technology developed along the way, inspiration for future scientists, occasionally direct relevance to understanding our own solar system's history. J1407b's ring system does connect to some of those benefits, particularly the parallel with our own solar system's early migration and water delivery. But the deeper motivation running underneath years of careful modeling work wasn't practical application. It was something closer to a refusal to leave a real question unanswered, simply because the object in question would always remain out of reach. Deciding that a place worth understanding doesn't have to be a place worth visiting reflects a specific kind of respect, extended toward an object that will never know it's being studied, that offers no practical return, and that exists entirely indifferent to whether anyone on Earth ever notices it at all. Studying something under those conditions, with no possibility of contact and no expectation of benefit, is one of the purer expressions of curiosity available to a species capable of reasoning about places it will never touch. Consider how much human effort goes into preserving detailed records of events, people, and places that no living person will ever personally witness or meet. Archives, museums, historical scholarship devoted to periods separated from us by centuries. Nobody questions the value of that work on the grounds that the events themselves are unreachable. J1407b asks the same question turned towards space instead of time. Does understanding require access, or is understanding itself a form of respect that doesn't depend on ever standing in the place being understood? If that moon does eventually consolidate into a stable, permanent body, orbiting a planet whose classification remains genuinely uncertain, it will do so entirely unwitnessed by anyone capable of appreciating what happened 434 light-years from the only species currently aware the process is underway at all. The astronomers who modeled this system won't live to see that moon's final form. Neither will anyone reading or listening to this account tonight. What they will have contributed, and what this account carries forward, is the recognition that the process happened, correctly modeled, honestly described, held with the same care, as if direct confirmation had been possible. This connects to a broader tension inside how humans relate to scale itself, one this entire journey has circled back to repeatedly, without naming directly until now. Every number in this account, the ring's width, the star's distance, the light's travel time, exists partly to communicate real physical facts, and partly to test something about human cognition. Numbers this large don't fit comfortably inside ordinary human experience. A mind built to judge distance in footsteps and time in seasons has no native intuition for 434 light-years, or for a ring system spanning 0.6 astronomical units. Every analogy offered throughout this account, the jump rope, the shadow through Venetian blinds, the elevator scale, exists specifically to bridge that gap, translating an inhuman scale into something a human nervous system can actually hold. Studying J1407b required accepting, from the very beginning, that no confirmation beyond careful modeling would ever be possible, that no spacecraft would ever verify the ring structure directly, that the forming moon would finish its process, whatever that process turns out to be, entirely unwitnessed by anyone alive today or in any foreseeable future. Pursuing that understanding anyway, with the same rigor and caution normally reserved for questions with clearer practical stakes, reflects something genuinely admirable about how a small number of researchers chose to spend a portion of their working lives. If understanding something we will never reach, never visit, and never directly confirm still counts as real knowledge worth pursuing carefully, what does that say about the value of understanding itself, separate from whatever practical use it might someday provide? Everything gathered so far, the ring's width, the moon's inferred mass, the years of restrained language from 3 careful researchers, exists because a small number of people decided a distant, unreachable object deserved the same rigor as anything closer to home. That decision has consequences that extend well past J1407b itself, into how the entire field of exoplanet science now approaches a category of world it barely had language for 2 decades ago. Before 2012, planetary science divided the universe into familiar categories, inherited almost entirely from studying our own solar system up close. Rocky planets, gas giant, moons. Rings, understood as a feature that happens to gas giants late in their lives, thin and settled, the way Saturn wears them now. J1407b didn't fit cleanly into any of those categories, and the discomfort that misfit created turned out to be productive rather than merely confusing. Consider what changed in how astronomers describe planetary rings once J1407b entered the conversation. Ring systems had always been treated as a minor feature attached to a planet's identity, something you mention after establishing mass, orbit, and composition, almost an afterthought in most planetary descriptions. J1407b's rings weren't an afterthought to anything. They were, for a period, the only confirmed thing about the object at all, more precisely measured than the planet's own mass or classification. That inversion, rings understood in more detail than the planet they surround, had never happened before in the history of planetary science, and it forced a real methodological shift. Researchers studying exoplanet rings now routinely start with the ring structure itself as primary data, rather than treating it as secondary confirmation of a planet already characterized through other means. That shift connects to something happening in parallel across a different corner of astronomy, the ongoing search for exomoons more broadly. For most of the history of exoplanet detection, moons around other planets remained almost entirely theoretical, too small and too faint to detect directly with any instrument available. J1407b's ring gap offered something different, an indirect but physically grounded method for inferring a moon's presence and rough mass without ever needing to see it. Researchers working on exomoon detection elsewhere in the galaxy have since adapted that same gap analysis logic, looking for similar disruptions in other circumplanetary material as indirect evidence of satellites too small or too distant to observe any other way. Kenworthy's team didn't just solve one puzzle about one object. They demonstrated a reproducible technique, testing physical models against light curve data until the fine details match that other researchers could apply to entirely different targets without having to reinvent the underlying approach from scratch. Science rarely advances through isolated discoveries treated as endpoints. It advances through methods that outlive the specific case that first proved them useful, carried forward by researchers who never worked directly on the original system at all. That pattern raises a genuinely open question about scale. If ring systems like J1407b's exist elsewhere in meaningful numbers, current detection methods are only capable of finding them under a narrow set of conditions: a young star, a ring system still wide enough to matter, and critically, an orbital alignment that happens to cross our specific line of sight from Earth. Every one of those conditions has to align simultaneously for a system to become detectable at all. Relax any single condition, and the ring system remains completely invisible to every instrument currently pointed at the sky, indistinguishable from empty space, no matter how large or how actively it's building moons. Estimating how many ring systems might be hiding behind unfavorable geometry requires a specific kind of statistical reasoning astronomers have applied to other detection biases many times before. The same logic explains why early exoplanet surveys found so many planets orbiting extremely close to their stars. Not because close orbits are unusually common, but because close orbits produce more frequent, more easily detected transits, biasing early discoveries toward exactly the systems easiest to catch, rather than the systems most representative of what actually exists. Applying that same correction to ring systems suggests the true population. If J1407b's formation process turns out to be common rather than exceptional, could be considerably larger than the single confirmed example currently on record. None of that estimate can be confirmed without more data, and stating that limitation plainly protects the integrity of everything built on top of it. What can be stated with confidence is narrower but still significant. The methodology proven on J1407b works, tested against real data spanning 56 days, and confirmed independently by researchers approaching the problem from different institutions and different starting assumptions. That methodology now exists as a permanent tool available to anyone searching archived or future survey data for the next example, whenever or wherever it happens to surface. The story of J1407b isn't only the story of one ring system around one distant, ambiguously classified object. It's also the story of how careful, patient methodology, once proven on a single difficult case, becomes something an entire community of researchers can reach for the next time. Something equally strange shows up in their own data, no longer facing the same 3-year gap between recording and recognition that delayed this particular discovery the first time around. That acceleration matters more than it might initially seem. The 3 years between when SuperWASP first recorded J1407's strange light curve and when Picot finally opened, that specific chart represented years during which the discovery simply sat, unrecognized, in an archive. Nobody had reason to search specifically for this kind of signal. Researchers now searching for similar systems don't face that same blind spot. They know what to look for, they have algorithms built specifically to find it, and they have a proven modeling technique ready to apply the moment a promising candidate surfaces. Whatever the next ringed exoplanet turns out to be, wherever it's hiding in already collected data, or in observations not yet made, the path from initial anomaly to confirmed discovery has already been shortened by everything learned here. If a single unusual chart ended up reshaping how an entire field searches for a category of object it barely had language for 2 decades ago, what does that suggest about how many other quiet, methodological revolutions are currently sitting inside datasets nobody has yet had the reason or the patience to search closely enough to find? Every question this journey has opened, the mass still uncertain, the moon still unconfirmed, the orbit still resisting a clean label, gets left exactly where it belongs tonight. Open. Not because the answers don't matter, but because leaving them open is the most honest place to end a story built entirely on careful, incomplete evidence. Every confirmed fact in this account came from someone refusing to guess past what the evidence supported. Picot refusing to dismiss an anomaly as noise. Mamajek refusing to announce rings before the modeling existed to prove them. Kenworthy refusing to claim a moon's existence when a gap could only suggest one. That same refusal extends to how this account ends. No tidy resolution gets manufactured here simply because a story wants one. The uncertainty stays, because the uncertainty is real, and real is worth more than tidy. Return for a moment to the number that opened this entire account, 200 times larger than Saturn's rings. That comparison worked because Saturn is close enough, familiar enough, to hold in the mind without effort. J1407b's rings never had that advantage. They exist only as a reconstruction, built from 56 days of dimming starlight and years of careful modeling, a structure nobody has ever seen and nobody ever will, standing in for something real that continues, right now, whether or not anyone on Earth is thinking about it. The ring system doesn't need us to understand it correctly. It doesn't need the modeling to be right, doesn't need the exomoon hypothesis confirmed, doesn't need any of this careful, patient reconstruction to match what's actually happening 434 light-years away. The rings will keep thinning, the moon will keep accreting or not accreting. The whole system will keep drifting toward whatever future it's heading toward, entirely indifferent to whether human instruments ever manage to watch it happen. Understanding, in a case like this, isn't for the object being understood. It's for us. That distinction matters more the longer you sit with it. Most of what gets called scientific discovery carries at least some practical shadow, a technology developed along the way, a health application, a defense concern. J1407b offers almost none of that. Its only return on the years spent studying it is the understanding itself, a fuller, more accurate picture of how giant planets and their moons come together, held by a small number of researchers and, now, by whoever has stayed with this account long enough to reach its final act. That's not nothing. It's actually one of the purer things a mind can do. Spend real effort understanding something that will never know it was understood, purely because understanding, on its own, still counts as worth having. There's a specific physical fact worth returning to now. Every atom heavier than hydrogen and helium in your body the calcium in your bones, the iron carrying oxygen through your blood right now, formed inside a star that died before our solar system existed. That star's death scattered those atoms across space, the same way J1407b's rings are scattering material now. Some of it destined to become part of a moon, some of it destined to be flung elsewhere entirely. If this system ever undergoes the kind of gravitational rearrangement our own solar system experienced billions of years ago, the process forming a moon around a planet 434 light-years away and the process that once assembled the atoms in your own hands aren't separate stories. They're the same physics, running at two different points along an almost incomprehensibly long timeline, one still actively unfolding, one long since finished and settled into the shape reading or listening to these words tonight. It's the literal mechanism by which every planet, moon, and body in the universe gets built. Gravity slowly gathering scattered material into something coherent, whether that coherent thing is a 200 times larger version of Saturn's rings or a human heart, still beating. Slower now than it was at the start of this account. If this account has done the quiet work it was built to do, a camera recording starlight it didn't understand. 3 years of that recording sitting unread. A graduate student choosing to look closely instead of moving past it. A cautious paper that claimed exactly as much as the evidence allowed, and not one word more. Years of modeling, adjustment after adjustment, until a physical structure finally matched the fine texture of a light curve nobody had fully explained before. A decade of waiting for a second transit that hasn't happened yet, may not happen for years still, held by researchers and amateur observers alike who committed real attention to an event with no guaranteed reward. None of that required certainty. All of it required patience, applied consistently, by people who understood that real knowledge about something this distant would only ever arrive slowly, one careful inference at a time. That's the shape this account has tried to hold from its very first sentence tonight, all the way through to this one. Not a story that answers everything, but a story that shows what it actually looks like to take an unanswered question seriously. For years, without rushing toward a conclusion the evidence hasn't earned yet. Whatever J1407b turns out to be, planet or brown dwarf, bound or drifting free, its rings intact for millions more years or already unraveling faster than current models suggest, the answer will arrive the same way every answer in this story has arrived so far. Slowly, carefully, built by someone willing to keep looking long after the initial excitement of a strange chart has faded into the quieter, harder work of actually understanding it. You've stayed with all of that tonight, through 56 days of dimming starlight, through a moon that may or may not exist, through a planet that may or may not belong to its own star, through 434 years of traveling light, finally reaching whatever room you're lying in right now. That kind of attention, sustained across a story this uncertain, this patient, this willing to leave real questions open rather than force them closed, is its own quiet form of the same discipline that built this discovery in the first place. Thank you for staying with this one all the way through. Rest well tonight, and let the rest of it go.